Well, I hope you guys miss me because I sure miss myself. I'm back again in my sound generation journey. I just went over some of the older videos, and it seems like I've done a whole bunch of things, like trying to use code books. Uh, I'm gonna be honest, I only read the last video where apparently I used a code book, and I thought that would fix my issue. And you don't really know much, and the more you learn something, the less you know, and the more you know that you didn't know much before. Suffice to say, I've done some work, and this right here is my version control system. This is very high tech, and I've been really using all of these versions at some point again. Surely they're not here for no reason at all. That will be weird. Anyway, made a new network design, and what I've done, because my goal has always been to roughly combine neural processing and audio in a useful way. And what that came down to is wanting to achieve sound morphing. I haven't really gone there yet, but to do that, it needs to be human editable. There needs to be a person there, and the person needs to be able to use controls, some type of interface that he can understand, and that I can understand. And we want to design our system to be humanly understandable. Now, in my previous designs, there was none of that. I had a code book. I understood what it was doing, but I didn't really. The system itself wasn't really parameterized. You couldn't really edit anything. There was no real generalization from what I remember. But it's been like 1 month or 2 months. I don't remember. And I've tried a whole bunch of new approaches. Now, this approach, after I'm not gonna lie, it's not like I directly came up with it. I had a bunch of concepts in my head on how to approach this. And one of them was, okay, but what I want is for my network to talk to a synthesizer. Now, my dream has always been to create a new digital audio workstation, but for the use case I was going for is, okay, let's say I make a basic synthesizer. I want the neural network to use this synthesizer to produce a sound. As a matter of fact, to recreate a sound. Now, it turns out that idea isn't new, and it's actually the most logical step to take if you want to integrate AI into sound editing. You need to have actual controls. But what I also thought is, okay, but that might be a bit too basic. So I want to have a layer where it takes in a sound, it learns to extract useful information from sound files, just the most useful ones. It turns that into a space, like a library of all types of sound bits, and then it will use that to compose a sound, and that composition is what's turned into the synthesized sound. Great. So if you've worked with this stuff before, and if you're much smarter than me, which I'm sure all of you are, you're thinking to yourself, this is DDSP. This guy is just stealing Google's idea because I was just sitting here and I just came up with something a $1 billion company came up with. Well, no, because what I did is I talked to GPT. I'm a little embarrassed to say, but I talked to GPT. I did more than just talk to GPT. Let me put that. I did more than just talk to him, but I discussed these ideas. Like, look, conceptually this makes sense, so it should be possible. And he was like, yeah, like Google has done this, and Jukebox has done this, and all these big companies, and apparently all of it exists already. And I'm gonna be honest with you, it's very validating to have an idea, to find out that you're not the only person with this idea, which for me is just proof that my idea isn't crazy, but then also that there's working versions of this. So I set myself to work out this idea, and I've implemented it as a set of stages. Now, I haven't named the stages per se yet because I'm not entirely sure if the design is complete. There's a lot that's going to change, but right now we have a processing stage, a mapping stage or encoding stage, a controller stage, and a synthesizer stage. So to lay out how it works, the processor takes in sound and it creates three types of data. Very high quality version of the sound file, but a very low temporal context. So it sees, or very high temporal context. I don't really know which word it is exactly, but it sees high detail, but in very short time spans. Then the middle version is, as you might understand, a bit better, a bit less quality, but a bit more time. And then the lower version is just very low quality, but like a very long time span. And what this creates is a bottleneck. The network is going to use these three different qualities to reproduce a sound. So it's going to have to use the lower version to reproduce the more of the timeline. It's going to have to use the middle one for whatever it thinks is relevant for that. And it's going to use the higher one to get the exact crispy details of a sound. Ideally. Now, all of this is up to how you configure the network. There's a lot of debugging. It's really not that simple and magical as just create these three and it works. But after it's been able to gather the useful data on a slow, mid, and high rate, it passes that data into an encoder or mapper. The job of this thing, ideally, is to take this data and turn it into a representation on a manifold. Basically, it writes a book to make this data that's kind of like this and this and this, and then it just poops it out there. And then I ask it to recreate the sound, but in this manifold space that it has created, and I get a timeline. And the timeline is frames, it's not samples. I have a lower frequency version, a frame rate version of the sound that's represented as tensors. Once I have these tensors, I send them to a controller whose job is to turn frame-based tensors, like this semantic tensors, I don't really know what the name for it is, into actual synthesizer controls. So then I have a frame representation of the synthesizer controls, which is called parameterization, I suppose. And this is sent into an actual synthesizer. Now the synthesizer is not complicated, guys. It's just amplitude, frequency, and harmonics. You can make the synthesizer as complicated as you want. You can add all of these things, but at the end of the day, sound is basically just amplitude and frequency, and then harmonics is just an easier way to create more complex sounds. Right. So now you have in most cases, a very flat representation of your sound. It depends how big your data set is, how complicated the sound is that you're making, but the synthesizer can't perfectly capture the very fine details of the real world, especially not of the real wave files. Now in my use case, I don't really have that issue. I feel like it's fine. But if you want to go a step further, you then create a refiner that takes this synthesized sound, looks at the original sound, looks at the semantic information, and then realizes, oh, okay, so he's not really good at representing this particular aspect of the sound, so I'm going to add it to the output, and then your sound is better. It's risky to do this, because this vocoder really is what it is. It might actually learn to completely take over the sound generation, and you're back at the starting ground where you have no way to edit your sound because it's just memorizing it. Great. Another issue. To do morphing as you and I understand it is to take one concept, take another concept, and to make a concept that mathematically or at least conceptually seems in between. So you've seen the things online. A guy renders a bed, and the bed is either made out of water, it's made out of leaves, it's made out of fire, it's made out of lava, but it's still a bed, and there's still lava. But conceptually, it seems to be in between. To do this in sound, you actually need a trajectory. So this is how this sound plays out. Now, luckily, we have this. It's called a semantic timeline. We already have the basis for this. But it's complicated because we want to change the timeline itself. not the bits that make up the sound, but the way the timeline evolves and the bits it's using, and then find an in-between version between two sounds. I don't know how to do that yet. I haven't been able to create a working version. It's just been difficult. And I don't really know what else to comment on this except that I'm working on it. Right, so let's now see this in action, because we have the timelines, so we should be able to go in a sound and mix two sounds together. Just to not talk much longer, the top is the splash sound, the bottom is the step sound, and this is a basic curve editor that allows me to choose when to start playing a sound and how much of one particular sound I want. It's a very low dimensional version of this manifold space, I guess. I'm going to count down to 0 and it's going to play the sound, so prepare your ears in case it's too loud. 3, 2, 1. That must have been very loud from what I saw in, in my recording software. And now I'm going to kind of mix it to the water splash, like so. 3, 2, 1. You can hear that the water splash is playing at the same time. And if I put it at the ending, you can hear that it actually adds it back. So this is a very intuitive way to play around with the sounds, but for all practical purposes, it just sounds like a gain, right? It just sounds like a gain. Like, okay, I want to have this sound playing this loud, the other sound playing that loud. Now, for me telling you this is actually blending the sounds together inside of the network, but to human ears, it just sounds like a basic gain function. So there's nothing special here yet, because the issue is, I am multiplying the features by a static number, but the features are higher dimensional. They're not just one feature here, one feature there. Each one of these little dots has 128 numbers that make up the sound at this specific frame. 128 numbers. So how do you logically represent this? Because I want to edit on each frame how much of a particular aspect of the manifold is activated. Well, we're in luck, because this is a very simple network. It is basically just every frame we have 128 numbers. So we can represent this as a 2D geometry. But the number is another dimensional axis to it. So it's a 2D geometry, but it needs another dimension for the activation, the amount of activation. Now, you probably already know what I'm gonna show you, but I was just blown away by the fact that I could visualize this in my head. This is what it will look like if we had, for every time frame, a set of controls per feature. So now, this is not the start of the sound and this is not the end of the sound. This is the start of the sound and this is the end of the sound. And the left to right is the features inside of the network. And the top and the bottom are going up and down. That is the amount of activation per feature. Now, what is a feature? Honestly, very hard to explain, because a feature is just how the network learns to represent a particular sound. And if you give it a huge amount of data, it needs to be able to map all of that data to 128 features. And that's how kind of generalization happens, because it has not enough information to memorize the data, so it's going to have to share the features. And usually it does this in a way where the features are highly optimized. They're not intuitive, but they're optimized. So it will try to use as much as possible in one area. Now, you can train it to force similar features together, but you can't really map it to a human understanding. Not all the time. And so when you use a synthesizer approach the way I did, it sort of becomes more humanly interpretable. Now, how would you edit this? Well, my idea is to have a type of terrain editor, because this is a type of terrain. And when I move the terrain up here, I'm saying, okay, at let's say 25% into the sound, more of these features are activated, more of these features are activated. Now, how do you know which features to turn up and down? That's basically a creative process, but also a process of the network, if it's actually interpretable and coherent. But also, you could do this by loading in two sounds, because this, besides being a good way to edit the semantic representation of the sound, is also a representation of the sound itself. So if you had two of these sounds, I think I jumped a bit there in terms of thought, but this does not only provide a useful way to edit the sound, it's also a useful way to visualize the sound, because this is just what the splash sound looks like over time, according to the network. Now, obviously, I have 12,000 time frames, and this program does not like rendering that much, so I made it 128 by 128 instead. I basically stretched it, or whatever you call it. So as far as the network is concerned, we can now visualize what it's really doing in the sounds. So here comes the crux of the issue, though. It's we have multiple places we can edit the generation of the sound. We have the audio processing area, where we can decide this much of the low temporal features, this much of the high temporal, this much of the mid temporal. But we also have the area of the semantic map itself, because this is just a representation of the sound after it left the encoder, the mapper. But we also have the pipeline before that, where we sent in the sound, and we can mess around with the amount of activation in each of the temporal details. But we can also mess around with the actual parameters, because ultimately, as a sound producer, you want to work with real parameters, with knobs, with this much amplitude, this much frequency, this much harmonics, and a bunch of other options you can add in. So to make this a full-blown editor of sound, you need to be able to have a pipeline where you edit the sound going in, the sound being transferred, the sound being made into a timeline, and the actual synthesizer parameters. And then in between, even how much of one particular sound at one particular point. There is so much possibility for editing here that it's really hard to not get feature creep. I think that's the word for it. To not want to make too much, but to also make it useful. That is to say, we can also edit the timelines themselves. Right? Because we can change how much of one particular tensor is at a particular point. So that means we can also make our own sounds based on this map. Because each particular point is a type of sound. And this representation is the timeline. So I'm not sure yet how to go from here. I have so much hope for this. The only thing that's left is a trajectory generator, one that learns to make the timelines so that we can make new and unique sounds out of the timelines. And then maybe making the manifold more meaningful. I am very sorry if I jumped from one line of thought to the other one, because there's so much to discuss, and I feel in so many ways so out of place in this area of work. I feel like I should be much smarter for this, but I just wanted to show off the progress so far. I'm very happy to have a synthesizer, very happy to have a pipeline that allows me to add in information per sound, to shape the manifold better, to have a synthesizer that I can play around with. And for now, a very simplified GUI, because I to make the actual audio workstation, I'm probably going to have to move to something like Vulkan to get very high performance in the graphical views. But we're not there yet. We're not there yet.